Everyone. In this video, we're going to look at solving separable differential equations. So that's a differential equation in which I can separate one of the variables from the other variable, and each expression, so an expression of y will be with its differential dy, and an expression for x will be with its differential dx. So essentially, I create an equation where I can integrate both sides with respect to the two variables. So in this instance, for example, I could rewrite this equation dy dx equals y squared as 1 over y squared dy equals dx. And note that's why I've given the restriction that y doesn't equal 0, because I had to divide by y squared. If I didn't give that restriction, I would essentially be introducing that restriction in order to solve the differential equation. But now that I have it separated, I can integrate the left-hand side with respect to y and the right-hand side with respect to x and get a solution. So antiderivative of 1 over y squared is negative 1 over y plus some constant. I'm going to call it c1. And antiderivative of 1 with respect to x is x plus some second constant. Now, in practice, I don't actually need two constants. I could simply combine them. So what we really do in most cases is we would write negative 1 over y equals x plus c, where c is the combination of the two constants from the two integrations. This means that y is equal to negative 1 over x plus c. And since I don't have an initial condition, I can't solve any further than that. This is just the general solution. Notice that unlike the differential equations we've been solving up until now, the solutions are not just vertical translations of each other anymore. In fact, these ones are horizontal translations of each other, but the placement of the constant is going to vary depending on the method used to solve the differential equation. The constant appears at the integration step, at the antiderivative stage, and then it has to just get manipulated in as you're isolating y. So let's look at another example. In this case, we have a more complicated differential equation, but we still can separate the variables. So I would turn this initially into dy dx times x squared minus 1 equals negative 2y, which if I just multiply by the dx, then I've got dy times x squared minus 1 equals negative 2y dx. This is the wrong variable expression with the wrong differential. So we divide both sides. Now I'm going to divide out x squared minus 1. I can leave the minus 2 or I can divide it out. It doesn't really matter. I'm just going to divide by y, not by negative 2y, because ultimately I'm going to want to isolate y anyway, so I might as well kind of get started on it here. So I end up with 1 over y dy equals negative 2 over x squared minus 1 dx. So at this point, we have separated our equation, so I can antiderive, I can integrate on the left with respect to y and on the right with respect to x. Straightforward on the left-hand side, we've got the natural log of the absolute value of y. I'm going to just put y here because we're not going to worry about the nuance of absolute value of y in this course when we're trying to isolate the y later at the end. And I'm not going to add a constant on this side because I'll just add it on the other side. Now, for this particular fraction, we need partial fractions. So if I break this up, this actually is equivalent to the antiderivative of 1 over x plus 1 minus 1 over x minus 1 with respect to x. I'll leave it to you to check that I've broken those up correctly, but from here, that gives me the natural log of x plus 1. Again, not going to bother too much with the absolute values at this stage, minus the natural log of x minus 1 plus some constant. Now, I am going to call it C1 because as we manipulate, I'm going to simplify some things that are just constants. And actually, what I'm going to do, I'm going to call this the natural log of C, because natural log of a constant is just another constant. So that's just a form that's going to allow me to simplify the right-hand side a little nicer. This gives me the natural log of essentially c times x plus 1 divided by x minus 1 as my argument, because then I can more clearly or more easily simplify and turn this just into y equals c times x plus 1 over x minus 1. That then is the solution or the family of solutions to this differential equation. So how you treat the constant can vary depending on what you're going to need to do with it. So I put it in a natural log simply so that I could combine it with the others. And now looking at a final differential equation that is separable, but this time where we'll have an initial condition. So to separate this out, I get 1 over y dy equals x squared dx. Both fairly easy things to integrate, so that's nice. We take the antiderivative. Oops, it didn't switch to red. Oh well. We get natural log of y equals x cubed over 3 plus some constant. I'm going to isolate the y before I solve. I guess it doesn't really matter. But this is y equals e to the power of x cubed over 3 plus c. I'm going to call that C1 because the reason now, if I didn't have an initial condition, I would simplify this one step further. I would write it as y equals c times e to the power of x cubed over 3. Because of my my exponent laws, this is the same thing as e to the power of x cubed over 3 times e to the power of c1. And e to the power of c1 is just a new constant. So this is the more common form for writing this differential equation. I do have an initial condition, however, and I could have substituted that in much earlier in the process. So I could substitute it in right here, or I could substitute it in right here. I'm going to, now that I have it simplified, might as well substitute it here. So 1 equals c times e to the power of 8 over 3. So, did I do that right? Yeah. So then c equals e to the power of negative 8/3, basically. Which means that I can write this as y equals e to the power of negative 8/3 times e to the power of x cubed over 3. In this case, it would have probably been simpler had I found c at this point, but I wanted to show you that when I'm giving the general solution, this is the form I would give. In this case, now that I do know what c is, I'm going to combine this and write this as y equals e to the power of x cubed minus 8 over 3. That is the particular solution in this instance.